I'd like to talk with you about special sequences called geometric sequences. Let me give you an example of a geometric sequence. 5, 10, 20, 40, 80, 160, and on it goes. Can you see how we could get from one term to the next by multiplying by 2? 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, and so on. Another way of finding that number is taking any two consecutive terms in the sequence and dividing. 10 divided by 5 is 2. 20 divided by 10 is 2. I can jump over here. 160 divided by 80 is 2. It is the same ratio regardless of which two consecutive terms you grab. So we call it the common ratio. So for this first sequence, the common ratio is equal to 2. Let's look at another sequence. 72, 12, 2, 1/3, 1/18, 1 over 108. And can you tell what you do to get from one term to the next? You might look at this and think, well, I'm dividing by 6. We certainly are, but equivalent to dividing by 6 is multiplying by 1/6. If we take 72 and multiply it by 1/6, we get 12. Multiply by 1/6 and we get 2. Multiply by 1/6 and we get 1/3. Multiply by a sixth again and we get 1/18. And so on throughout the sequence. And if you didn't identify what the common ratio was, and you knew it was geometric, you could grab any two terms. I'd grab the easiest ones. For me, it would be this 2 and this 12, and divide. 2 divided by 12 is 1/6, so we know our common ratio is 1/6 for this sequence. Let's look at one more. How about 385, negative 38.5, positive 3.85, negative 0.385. Do you see how we get from one term to the next with this sequence? Do you see that they're alternating? So we're going to be multiplying by a negative number each time, so they'll alternate. So if we multiply by negative 0.1 or negative 1/10, we'll get from one term to the next to the next. And again, to find the R value, you can grab any two consecutive terms. So I could take negative 38.5 and divide that by 385, and you would find that's negative 1/10. So that's our common ratio. And every geometric sequence has a common ratio. Now that we know that a geometric sequence is a sequence in which there is a common ratio, we can use that to determine whether a sequence is geometric. So let's look at these two examples. The first one is 2, negative 10, 50, negative 250, and 1250. Is that sequence geometric? Well, let's see. We're looking to see if there is a common ratio. I take a negative 10 and divide it by 2, and I get negative 5. If I divide 50 by negative 10, I would also get negative 5. Let me take the next two consecutive terms. Negative 250 divided by 50. That is also negative 5. And last in our list, we have 1250 divided by negative 250. That would also be negative 5. So you'll notice that is a common ratio. So the answer to the question is yes. This is a geometric sequence. Now let's look at our next one. Do we have a common ratio for this sequence? Well, we'll take 1/3 and we'll divide it by a half. we know that's equivalent to 1/3 times 2 over 1. So we have a ratio of 2/3. Let's look at the next ratio. 1/4 divided by 1/3. That is 1/4 times 3 over 1, and we have a ratio of 3/4. So the ratios are not the same. So we do not have a common ratio. We don't need to test any other ratios because we already know there isn't a common ratio. So we would say no, this sequence is not geometric. Now let's talk about how we'll find a formula for the nth term of a geometric sequence. Let's say these are the terms of our sequence. A sub 1, A sub 2, A sub 3, A sub 4, and on we go, and out here somewhere is the nth term, and we want a formula for that. Well, we know the first term is just A sub 1. And by the way, in some textbooks, you'll see that for the A sub 1, they just call it A and then put the subscripts on subsequent terms of the sequence. But let's move on to the next term of the sequence. If you know the first term, how do we get to the second term? Well, remember we multiply by r. So the second term of the sequence is the first term times r to the first power. Let's move on to the third term right here. How do we find it? Well, if we started with the first term, we would have multiplied by r to get to the second term, and then we would multiply by r again to get to the third term. So the third term is A sub 1 times r squared. Similarly, we'll multiply by another factor of r to get to the fourth term. So the fourth term is A sub 1 times r cubed. And look up here, I'll put another times r up here, and you can see from A sub 1 over to A sub 4, we multiplied by r times another r times another r. Notice our pattern. A sub 2 is the first term multiplied by r to the first power. A sub 3 is the first term multiplied by r squared. The fourth term is A sub 1 times r cubed. If we continue that pattern, what we find is that A sub n equals the first term times r to the n minus 1 power. So for a geometric sequence, let's write it right here. The nth term is equal to the first term times r to the n minus 1 power. And of course, this is a relationship if the sequence is geometric. So now let's try a problem. Given a geometric sequence with the first term equaling 2 and our common ratio equaling 3, find the nth term and the sixth term. And notice the notation as I was reading it. A sub 1 is the first term. R is our common ratio. The nth term is A sub n. The sixth term is A sub 6. So let's do it. When it's asking for A sub n, it's asking you for a formula that represents that nth term. And we know A sub n equals the first term times r to the n minus 1 power. Let's substitute in what we know. A sub 1 is 2, r is 3, and we raise that to the n minus 1 power, and there's no simplifying that I can do, so that one is finished. But now let's find the sixth term. We can just use the formula I have written there. So 2 times 3 to the 6 minus 1 power, or 2 times 3 to the 5th power. 3 to the 5th power is 243, and we multiply that by 2, and we'll have 486. So what we know, if we were going to list the terms of this sequence, first term, second term, third term, fourth term, fifth term, sixth term, the first term was given to us and we know it's a 2. Now we know that the sixth term over here would be 486. Let's look at this example. Find the 8th term in the geometric sequence, and we have a list of the first 4 terms of the sequence. Now, I don't need to test to see if it's geometric because it was stated in the problem that it's geometric. So I need to find R. Remember, to find R, we find 2 consecutive terms and divide. Now, I find whichever one seem easiest to me to use. I like the 6 and the 9. So I will take 6 and divide by the previous term. So the common ratio for this sequence is 2/3. So let's find the 8th term. We know the 8th term in a geometric sequence is found by starting with the first term and multiplying by r to the 7th power. Remember, this exponent here is 1 less than this subscript. So let's substitute in our values. Our 8th term is what we're trying to find. Our first term is 81 over 4. Our R value is 2/3, and we're raising it to the 7th power. Now, I want a nice exact value for this expression. I don't want a decimal approximation. And let me just show you a nice easy way to do the calculation without a calculator. At some point, you may need to do this without a calculator. I want you to look for these kinds of patterns. We know 81 is 9 times 9. That means it's 3 times 3 times 3 times 3. That is 3 to the 4th power. Similarly, 4 is 2 squared, and we're multiplying that by 2 to the 7th over 3 to the 7th. So this is not a bad arithmetic problem, even without a calculator. I have 2 to the 7th divided by 2 squared. That would give me 2 to the 5th in the numerator. Remember, you subtract the exponents. And I have 3 to the 4th in the numerator and 3 to the 7th in the denominator. And if we do that division, we would end up with 3 to the 3rd in the denominator. And simplifying, we would have 32 over 27. And we have the 8th term in this geometric sequence. Let's look at this example. Find the nth term of the geometric sequence that's listed. 2 squared is 7, 14. 14 squared is 7, 98. 98 squared is 7, and on it goes. So when it's asking for the nth term, remember it's asking for the formula for a sub n. And we know a sub n is a sub 1 times r to the n minus 1 power. Well, we already know a sub 1. It's our first term. It's looking at us right here. But what's r? Well, we're looking at a geometric sequence. It was told to us that it was a geometric sequence. So we can take any 2 terms and divide. I'm going to use this third term and the second term. So we would have 14 square root of 7 divided by 14. The 14's cancel, and we see our r value is just the square root of 7. And you could have grabbed any 2 consecutive terms and done the division to find that. So now let's write our formula for the nth term. It's a sub 1, which is 2 times the square root of 7, times the square root of 7 raised to the n minus 1 power. Now, we can simplify this. Let me write this a little bit differently. It's a sub n equals 2 times the square root of 7 times the square root of 7 to the n minus 1 power. Notice I've deliberately separated the 2 times the square root of 7 down here. Now remember, we're multiplying the square root of 7 to the first power times the square root of 7 to the n minus 1 power. Those are quantities with the same base, so we can add the exponents. 1 plus n minus 1 is just n. So another way of presenting this answer is a sub n equals 2 times the square root of 7 to the nth power. And the nice thing about this is you could confirm that this is correct. Pop in 1 for n, and you'll find that you get this term. Pop in 2 for n, you'll find that you get this term, and so on. But I wanted you to see this example because I wanted you to see how after we used the formula, we could do some simplifying to present the answer a little bit differently. Let's do one final problem. Suppose in a geometric sequence that a sub 2 equals 7 and a sub 5 equals 1512. Find a sub n. Now there are a few ways to do this problem, but here's what I'd like to do. Draw a picture of what's happening. We have a first term, a second term, third term, fourth term, fifth term, and we know the second term right here is equal to 7. And we know that the fifth term right here is equal to 1512. We're supposed to find a formula for the nth term. And we know the formula is a sub n equals a sub 1 times r to the n minus 1 power. The problem is we don't know a sub 1 and we don't know r. Let's think about how we get from one term to the next in a geometric sequence. I know from this second term here, I would multiply by r again, and multiply by r again, and I would get to the fifth term in the sequence. In other words, 7 times r to the third power would equal 1512. And now I have an equation that allows me to solve for r. Let's divide both sides by 7. So we'll have r cubed equals 216. And now we take the cube root of both sides. And we find that r equals 6. Now I'd like to find the first term. We know the first term multiplied by r would equal the second term. So if we substitute in 7 for a sub 2, and 6 for r, we can solve for a sub 1. So we find that the first term is 7 over 6. Let me just pop it in right here. 7/6. And I hope this makes sense to you. Remember, as we move to the right, we would multiply by 6 to find subsequent terms. Well, in reverse, when we move to the left, we could divide by 6. So if I take 7 and divide by 6, I should get to the first term, and that's exactly what we have there. Now we're ready to find the formula for the nth term of the sequence. We know a sub 1 and we know r. Let's substitute them in. So we have a sub n equals 7 over 6 times 6 to the n minus 1 power. But we can make this look a little bit nicer. Just as we did on the previous example, there's some simplifying that we can do. Because we know this is 6 to the first power down here in the denominator, and this is 6 to the n minus 1 in the numerator. And we can simplify these by subtracting the exponents. N minus 1 minus 1 means that we would have 6 to the n minus 1 in the numerator times 7, and that's equal to a sub n. In other words, a sub n is equal to 7 times 6 to the n minus 2. And we have the problem complete.